Alright, we're going to talk a little bit about something called scientific notation, but first I want to review powers of 10 here. We all know if I take 5 times 10, I get 50. Okay, sure. But another way for me to express that same thing would be to take 5 times 10 to the power of 1, right? That's what 10 to the power of 1 is, still a 10. That's another way for me to say the same thing. 5 times 100 we know to be 500. But another way for me to say the same thing, 5 times 10 to the second power, because 100 is 10 squared. 5 times 1,000. We know that to be 5,000. Another way for me to express that would be 5 times 10 to the power of 3. Okay? Scientific notation. Takes numbers, in this case large, we're going to get larger and larger as we go here, large numbers, and expresses them in this form here. Some number A, okay, which A is just going to be one number, and then I can have a decimal point and maybe 1 or 2 more numbers, okay, but only one number, one digit, and then a decimal point, and then again maybe 1 or 2 more, but then times 10 to some power, I'll call it n. Okay, that's our notation. Okay? 5 times, a 1 with 6 zeros, that's 5 times 1,000,000. We know that's 5 million. Well, I can just write it like that. 5 times 10 to the power of 6. It's going to give me 5 times 1,000,000, 5 million. Okay? So that's large numbers. Now, what about small numbers? And by small, I mean between 0 and 1. What if I took that same 5 and I multiplied it by 10 to the power of -1. Oh, baby. We got to stop and think a minute. In the last section, I said a negative exponent, like 10 to the -1, that's equivalent to moving it to the other part of the fraction and giving it a positive exponent. We wrote it like that. Right? I said a negative exponent, move it to the other part of the fraction and give it a positive exponent. So 5 times 10 to the -1 is really like I'm saying 5 times 1 over 10 to the positive 1, which is really like I'm just saying 5 divided by 10, and we know 5 divided by 10 is the decimal 0.5. Okay, so 5 times 10 to the -1, we're saying equals 0.5. So you see what I did? There's a decimal here. By multiplying by 10 to a negative power, it moved that decimal 1 space to the left. Okay, I didn't explicitly say it up here, but here I moved the decimal to the right, right? It was a 5, 1 shift made it a 50, 2 shifts made it 500, 3 shifts made it 5,000. Well, now I'm going to shift to the left. So 5 times 10 to the -2 power would be 0.05. 2 shifts to the left. 5 times 10 to the -3 power would be 0.005. 3 shifts to the left. Okay? So these negative exponents, and it's okay to leave them as negative exponents in scientific notation. That's really the only place we want to see those negative exponents. Okay, but that's the notation we're going to use. We're going to practice writing numbers in standard notation and putting them in scientific notation, and then taking them scientific notation and going back to standard. So we'll kind of work it both ways. So let's kind of look first at a scientific notation number. What if I had this problem? 2.6 times 10 to the power of 7. I want to turn that back into a regular looking standard number. Well, times 10 to the power of 7 means I'm moving my decimal 7 places to the right. The first place gets me past the 6, and then I need to have 6 more places. So I've got 6 zeros out there. Go back and fill my commas in. That's going to be 26 million. Okay? What about this one? 1.1 times 10 to the -4 power. Okay, well now I'm going to go 4 places to the left. 1, 2, 3, 4. I'm going to need 3 leading zeros, right? So it's going to be 0.00011. That's how I would express that number. All right, let's do a couple more. Let's take 7.4 times 10 to the 9th power, and let's expand that back out. Okay, so I'm going to move that decimal 9 places to the right. First place gets me past the 4. I need 8 zeros here. 1, 2, 3, 4, 5, 6, 7, 8. Go back and fill in my commas. I've got 7,400,000,000. Okay. 3.107 times 10 to the negative 6 power. I've got to move that decimal 6 places to the left. First place gets me past the 3, so I need 5 leading zeros. 3107. Okay? So that's how we'll take a scientific notation number and expand it back to standard form. If we want to start with standard form, you go to scientific notation. I want to turn that into 4.6 times 10 to some exponent. Well, I got to take the decimal from here and move it to there. How many spaces is that? 6 spaces, 10 to the 6th power. Okay? Or I want to take this number and I want to turn it into 2.3 times 10 to something. It's always 1 digit decimal point, 1 or 2 more digits. We'll round it off if we need to. Times 10 to some exponent. So I want to take that decimal and put it right there. 1, 2, 3, 4, 5, 6, 7 places. 10 to the negative 7. Okay? Real quick, a couple more. Let's do that one. 7.4 times 10 to something. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 0.1, 2, 3, 4, 5, 6, 7. Let's have 8 leading zeros. And then a 9, 2. That's going to be 9.2 times 10 to the, since I had 8 leading zeros, 1 more gets me there, negative 9. Okay? We do lose a little precision with a notation like this on the big numbers, okay? And if we look at a big number that's kind of an everyday prominence, maybe we don't think about it every day, but it's something always lingering over our shoulders, it's the national debt. Okay, the national debt's a big number. If you haven't paid attention lately, it's 23.5 trillion, more than that, 23.5, more than 23.5. There's a cool website called usdebtclock.org. Cool just because it shows you all this stuff. It's heartbreaking to go in there, but I pulled it up on my phone here. Let's zoom in. This is live. It shows all kinds of government expenditures, but the top left corner, come on baby, zoom in there. Oh, come on now. Don't let me down. There we go. National debt, 23,595,800,000,000, and then see how fast it's moving. It goes up about $30,000 to $40,000 per second. Okay, so you can't even dream of what am I saying? You can't even dream of getting any kind of exact, number at any given moment in time because it's changing so fast. But let me just write down, at one point in time we had 23,595,801,865,127.38. That was our national debt at one time, right? That should be a point there, sorry. 0.38 cents. 23,595,801,865,127.38, and you can't even see it all. Shame on me. There. I just obviously made up those tail end numbers because it's changing so fast I can't see it. But this is an awfully big, bulky, clunky number, right? To try to use that number in some kind of calculation would be ridiculous. What's important here? It's 23.5 trillion. That's what's important, right? The 38 cents certainly isn't important. $127 certainly isn't important. The 5,000, the 65,000, the 865,000, the 1 million, quite frankly, all the way up here to probably the 100 million digit place. This is all chump change. 100 million bucks. That's nothing compared to this. Right? So we're going to round it off somewhere. I'm going to take this decimal and I'm going to put it right after the 2. 2.3, maybe we'll just round it right there. 2.36 times 10 to some exponent. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 places. Okay? That's how I would write the national debt in scientific notation. Dropping all the precision of these dollars that you're changing so fast anyway, it doesn't matter. But even if they weren't changing, again, what's significant here? Well, I mean, what's important and what's really just a rounding error, pocket change, okay? This is the important number, okay. I like to do one other fun exercise with scientific notation. I'll let you see what happens to your calculator. And this is also going to let us do something that's going to be covered in a future video about unit conversions. Okay, and that's going to be covered on what would have been our last night of class, but I like to get a little jump start on it here. But I like to do it now for purposes of the calculator. And again, I don't have your exact calculator on what you're going to have on the exam, but we'll see what happens with my calculator. I like to get a big number in the calculator by calculating the distance in miles across the observable universe. Okay, now that's got to be a big number. How many miles is it across the whole universe? Okay, we need to have a little bit of information to do that, and I've looked it up here. The universe that we know, the observable universe, is 93 billion light years across. Okay, light year is a measurement of distance, not time. Okay, and it's not a character from Toy Story either. 93 billion light years across. That's what we can see out there in the universe. And I want to know how many miles that is. Now, yeah, we could just ask our phone how to convert light years to miles, but that takes all the fun out of it. All right, let's think about it. How far does light travel in 1 year? If we could figure that out, then we would just take that and multiply it by 93 billion, and we've got it. Okay, so we got to figure out how far light can travel in 1 year. So we need to know the speed of light. Okay, anybody? Anyone know the speed of light, top of your head? 186,000 miles per second. Staggering speed. In 1 second. 186,000 miles. Okay, I think if you run the numbers, light can travel all the way around the Earth, I think 7.5 times in 1 second. That's how fast it is. And even at that ridiculously fast speed, it takes 93 billion years to go all the way across the universe. That's how big the universe is. All right, so I want to put that, I want to calculate miles. I want to do that. So here's what we're going to do. I'm going to actually turn sideways to give us a little more room here. I'm going to take 186,000 miles per second, and I'm going to convert that. Okay, I know there are 60 seconds in a minute, right? 60 seconds per 1 minute. So if I multiply that number by 60, okay, my units cancel. That's why I'm doing this, to show you how units cancel. The seconds cancel, and now I'm going to have miles traveled in 1 minute. So I got to take the miles per second times 60. Well, if I do the same thing again, because I know there's 60 minutes in 1 hour. Okay, so now the minutes cancel, and I'm going to be left with miles per hour. Well, I know there's 24 hours in a day. So my hours are going to cancel. And I'm going to have miles traveled in 1 day. I'm going to ignore any kind of leap year here, and I'm going to say 365 days per year. So my days are going to cancel, and I'm going to have miles traveled in 1 year. If I calculate all these numbers here, 186,000 times 60 times 60 times 24 times 365, that's how many miles light travels in 1 year. But guess what? I got to travel for 93,000 million billion years. Okay, now I'm down on the next line here, but this years would be up in the numerator, so it cancels that year down in the denominator. So the only unit left on the board is miles. So I'm going to multiply all these numbers together. All right, let's do it. And watch what happens to my calculator. Now, any calculator, any decent calculator should do something similar. So 186,000. And I already screwed it up. Look at that. 186,000, okay, times 60, times 60 again, times 24, times 365, times 93,000 million billion equals 5.455. 5.455. But then look closely. Can we zoom in here? Okay, and then a bunch more digits, which I'm going to round off. But look at that little 10 there. You see that? Times 10, and then there's a big old 23 up there. 10 to the power of 23. That's how many miles. 5.455 rounded off somewhere times 10 to the 23rd miles. Okay, that's how big these exponents. You know, you may say, wow, an exponent of 23 doesn't sound that big to me. Well, miles across the universe is a pretty big, darn big number. 10 to the 23rd is a really big number. Okay, when you have a number up there in the exponent, it adds up fast. Okay. All right, cool. So again, that was kind of killing two birds with one stone. It lets us see what happens to the calculator, and it gave us a little precursor to all these unit conversions, right? I canceled all these units out. Units multiply together, and units cancel each other out, just like numbers do. Okay? So that is pretty good there. I highly, highly, highly doubt you're ever going to have to do a calculation involving scientific notation. I didn't see any mention of that on your exam, so maybe rather than me writing it out, let me bust open my book and we'll just look at one real quick. Here we're going to multiply two numbers in scientific notation, right? Well, you're just going to take 4 times 2 is 8, and you're going to take 10 to the 5th times 10 to the 9th, and you add those exponents and you get 10 to the 14th. Okay, so not that big of a deal. The only problem would be, and maybe I should just pull off here quickly. The only problem with something like that would be, what if I had this one? What if I had 6 times 10 to the 3rd times 5 times 10 to the 5th? Well, 6 times 5 I would say is 30 times 10 to the, I'm going to add those together and get an 8, right? But see, this 30 is no longer in proper notation because I'm only supposed to have one number and then a decimal point. So I really need to call that 3.0 times 10 to the power of 1. That's how I would write the 30, but then I already had a 10 to the power of 8. So it's really 3.0 or just 3 times 10 to the power of 9. So I had to make a correction, in other words. Okay, sometimes you have to do that. Same thing with division. Sometimes you might have to make a little correction. If we look at the one that, I might as well just do it. I had this problem next in the book there. This one's going to be a division problem. 1.2 times 10 to the 6th divided by 4.8 times 10 to the negative 3rd. Okay, a couple things to watch out for. When I divide the 1.2 and the 4.8, I'm going to get a decimal of 0.25. And when I divide these, I need to subtract them. So let's be careful. It's going to be 10 to the 6 minus negative 3, right? And minus negative is plus positive. So it's really going to be times 10 to the positive 9 power. Okay, but here I got to make a correction again because I want the decimal to be right there. So that's really 2.5 times 10 to the negative 1, just to correct the 0.25. But then I had it times 10 to the 9th. So it's 2.5 times 10 to the power 8. Okay? Alright, that's pretty good for scientific notation. We are going to pick up now with that dreaded factoring polynomials I've alluded to a couple times.